This is it, the last video of Discrete Mathematics CS54 by Prof. Greenberg. Got a couple more, I think, from Prof. Osborne coming. I just want to talk to you today about a couple of special classes of graph, right? Kinds of graphs that people care about. So there's 5 of them. Graphs that mark relations, connected and strongly connected graphs, bipartite graphs, complete graphs, and planar graphs. So I'm just going to go through and talk about a little bit of each of these. So let's start with graphs of relations. So the idea is if R is a binary relation on some set A, R, so this is a binary relation on A. Wow, terrible handwriting. R is a graph with nodes from A. Right, that's the idea. So let's do a couple. So let's start with equality is a relation on pairs of gnats. And then that would give us just self loops. So then we can be clear here, R is a directed graph. Okay, let's do another one. Let's do less than or, oh, no, excuse me. Less than or equal to. This is another relation on gnats. Right, and this is a little different. So we're going to have these same self loops. But then 0 is also less than or equal to 1. There's less than or equal to 2. There's less than or equal to 3. And so on. And then similarly, 1 has its own arrows. Less than or equal to 2, less than or equal to 3, and so on. Okay, let's do one last one. Strictly less than is a relation on gnats. Right, so then 0 is strictly less than 1, strictly less than 2, is strictly less than 3. 1 is strictly less than 2, strictly less than 3. 2 is strictly less than 3. 3 is strictly less than 5. Right? I'm not drawing all of the arrows here, but you can kind of see them. Okay, so you'll notice that this is a directed graph and that the first thing relates to the second thing. If we wanted to draw greater than or equal to, then that just the pointer on these arrows, on these edges, these arrows would just switch. Okay, so thinking of a relation as a graph lets you really quickly think about things like reachability, which is related to transitivity, right? Can I get from one node of my graph to another by chaining along the relation? You can think about symmetry as about, well, okay, who can reach whom? Reflexivity is about self loops. It's a really helpful way to think about graphs, right? People will talk about the graph of a relation to sort of talk about how different bits are related. You can then get to apply other graph concepts, things like degree and things like that, which are useful ways to think about your relations. People who are thinking about graphs of relations also often think, let me move all of this down just a tiny bit. There. Ooh, was bothering me. People also use this to think about other properties of relations like connectedness. So connectedness, so a graph is connected, you can find a simple, I'll talk about that in a second, path between every pair of nodes. Okay, the simple part says, well, look, if I can find an edge between a pair of nodes that uses a loop, I can just cut out the loop. So simple, you'll always find. People will often sort of want to be a little clear for connectedness. Like, okay, is there a path between Big Bird and Big Bird? Like, yes, by default, right? Like, you're already at Big Bird. Okay, so this graph is connected. Now, right, as is. So, but if we copied this, well, oops. Oh, poor Snuffleupagus. Let's include him. Her? I don't remember. It's a thing you're probably supposed to know. Let's explore this graph for a second. Get rid of the edges. I have to say, I'm not in love with this whiteboard program, but it does a pretty good job of grouping objects. Okay, so let's draw a graph that's not connected. So here's a simple graph. Disconnected. Why? Well, poor, lonely Oscar the Grouch. Right? There's no way to reach him. There's no edge between any of them. Okay. Um, what are some other ways that things could be disconnected? Let's try another one. This graph is directed and also disconnected. So if we start here, how might we get to the count? Excuse me, this is incorrect. This graph is not disconnected. We can get to the count because, well, look, we're connected. It's just we have to break the law. We have to go down a one-way street. We're going counter there. So this is not disconnected, but it is not strongly connected. Sorry, I got my examples mixed up. So not strongly connected. So when is a graph? A graph will be strongly respecting direction. Weakly or simply connected, ignore direction. Right? So for a graph to be disconnected, there literally has to be a node with no edges coming into it. But a graph can be merely weakly connected. If, okay, there's edges between everybody, but some of the directions on them matter. So for simple graphs where there's no direction, strongly and weakly connected mean the same thing. For directed graphs, strongly connected means that you need to always be able to get everywhere following the rules, right? Following the edges of the graph. Right. So one might talk about a connected or disconnected relation to talk about discontinuity or things like that. Okay, great. Bipartite graphs. A bipartite graph is a graph where you can split the set of vertices in two, and edges only go from one set to another. Right, so like our vertices can be in these disjoint sets. Right, let's maybe be clear. V1 intersect V2 is empty. And then our edges say, well, look, I only have edges from V1 to V2 and V2 to V1. Those are the only edges we have. Sorry about this ugly U as notation. Okay, so what are some examples about that? Well, one possibility is to talk about graphs where the nodes are in some sense heterogeneous, right? So here's one. On the left-hand side, I'll do lists of gnats. And I'm not going to draw all of them. I'll draw a couple of them. Right, and on the right-hand side, I'll do the natural numbers. And then my edges, I'm only allowed to go from one partition to the other. So I'll draw the edges and you can try to guess what relation I'm talking about. Okay, what relation is it? Cue the Jeopardy music. I gotta get a soundboard. I feel like Dora the Explorer. Say length. Good job! Right, this is the length relation where we're relating the length of the list on the left to its length on the right. And it's bipartite here because we're not relating any numbers to other numbers. We're not relating any lists to other lists. There's other ways to do this too. So another way to think about it is suppose you have a soccer football match, right? And we have the German national team getting completely hosed by the South Korean national team, as happened in the not too distant past. It was just devastating to watch. It was really awful. So what you'll have is you'll have a bunch of players here. You'll have a bunch of players here, right? More than 4 on each side. And then you'll have some relationship like who's covering whom, right? And it sort of depends, right? You'll have multiple people covering other people, depending, right? And it might be, okay, here's who the Germans have assigned to whoever. And then the South Koreans have a different setup, like maybe they're doing man on, right? Who knows? All right, this person's uncovered, and it doesn't matter because it's not like the Germans are even going to score any goals or anything. It's a devastating game. So here, the relation that we have is a sort of a matching relation. And this is a really common thing to have for bipartite graphs, this idea of sort of two groups and they're matching with each other. In algorithms, you'll learn about a classic algorithm called the matching problem, where the groups are, in the original formulation, men and women getting married. That one didn't age so well, turns out. Turns out not to be a great problem to give. So what they do now often is it'll be like med students and med schools. So here I have sort of members of one team and members of another team. There's a bunch of classic algorithms dealing with these kinds of bipartite graphs with this sort of like kind of funny legacy. So anyway, these are bipartite graphs. They come up all the time in computer science. Okay, 2 more examples. Complete graphs. Complete graphs are kind of a funny set of graphs. They're like definitely a mathematician's graph. Like they define them because you can define them, and that's kind of cool. So the complete graphs are just the complete graph K sub I is a graph with I nodes and simple edges between every pair of nodes. Okay, here's K sub 0. I drew it. It's in this box. Okay, that's dumb. Okay, here's K1. You'll notice I'm just going to exclude self loops. People usually exclude self loops in simple graphs. Okay, here's K2. And here you thought it was a mountain somewhere in Nepal. Nepal? Pakistan? Can't remember. Right, there's K2. Here's K3. Okay, I'm going to stop using the box because now I think it's kind of clear what's going on. Here's K4. Right. Here's K5. Cool. Okay, and then there's another category of sort of like the subcomplete graph. So people will do K sub ij. Right, so K sub ij is like a little bit different. So these are bipartite graphs, but still talking about completeness. So what you'll do is here you'll have I nodes, and here you'll have j nodes, and then this will be complete. So for example, here's K2, 3. Ooh, that's terrible. Right? Everything in these two nodes connects to everything in these two nodes. Here's K3, 3. Cool. Okay, so these are the complete graphs. They're things to have in your pocket, right? You want to be able to talk about them because they're convenient objects, but they're not so important. Okay, lastly, are edges called planar graphs, graphs that can be drawn on the plane. So these are precisely those that can be drawn where no edges cross, right? This is an important category of graphs. So if you think of, so there's this theorem, which I'll talk about in a second. Each country is a node. A border is an edge. Maps, without enclaves or whatever, are planar graphs. Right, so this is important for a problem called graph coloring. So given a map, color the countries. So bordering countries have different colors. Right, this is a practical problem that cartographers have that turns out to have really deep mathematical implications. For a long time, there was this four-color theorem / conjecture where people believed every planar graph, every map, without fancy enclaves or whatever, like countries inside of other countries, could be colored with only four colors. And this was practically true. Nobody found one that you couldn't, but nobody knew how to prove it. And then somebody wrote a computer program in the 70s. Appel was the name. And they showed exhaustively that it worked. And a bunch of mathematicians first said they didn't believe it, and then they said, well, if it is true, nobody could care. And then in the late 90s, early 2000s, Georges Gontier and his group proved this completely in Coq. Right, this was I think Coq's first big moment in the spotlight. It's had several since. And then mathematicians said, okay, well, look, we kind of have to believe it because Coq is sort of much more, we're more willing to believe that than just a computer program some guy wrote, even if he was very careful and it turns out correct. But that means this couldn't possibly be interesting because there's no interesting human proof. There's just big, long Coq proofs. So this is what I would call mathematical sour grapes, that a bunch of mathematicians got real salty about how computer scientists were eating their lunch. And I think it's just a thing they should get used to. Okay, with that shade throwing out of the way, there's another great theorem that's kind of cool that says, okay, there's this concept of subgraph where it's like, okay, if I take a subset of vertices and subset the corresponding edges, that's a subgraph. And a graph G is planar so long as this guy, pentagram there being quite appropriate, and this guy aren't anywhere included. Right, that's sort of an exact characterization of graphs that are planar. These two graphs, K5 and K33, sort of characterize like knots, like triangles that can't be broken. Right, you sort of get I would phrase it maybe like a triangle of triangles that you sort of like can't undo, and then there's no way to draw those edges. Is my intuition. The actual mathematics is really complicated. Okay. So that's all I wanted to talk about. These are just the concepts of graphs that are worth knowing about, being able to have these graphs in your toolbox. Let me draw that a little thicker. If you have questions about these, as usual, we'll be on Piazza. Feel free to ask us about what's going on there. I hope this was informative. I hope these definitions are interesting to you. You can look forward to years of thinking about things in terms of graphs. Especially if you go on in computer science, but even without it, this is, I think, just a really, really useful metaphor. Okay, that's it. Post your discrete homework questions online. I think Combo is due today, Friday, May 1st. The discrete homework is due a week from today, and then after that we'll have the final. The final is scheduled to take place on Wednesday. We've given you a 12-hour window. If that 12-hour window is not going to work for you, you need to let us know by next Friday for us to reschedule that for you. So please let us know as soon as possible. It's not a big deal. We just need to know in advance so we can do the planning appropriately. Okay, thanks so much, everybody. It's been fun making these videos. I hope it's been fun watching them. The only thing that would have been more fun would have been getting to do this in a classroom with y'all. Okay, take care of yourselves.